So in this video, I'm going to be discussing the assignment and the topic of Module 1, topographic maps, what they are, how we use them, how they're constructed, why they're useful, how to interpret them, etc. So a topographic map is a very clever way of depicting the three-dimensional landscape, the three-dimensional shape of the surface of the Earth, on a two-dimensional flat map. That three-dimensional information is contained in all of the brown squiggly lines on this map. This is a topographic map of the Tucson area. And in some parts of the map, such as up here in the Catalina Mountains area, there are a lot of these brown squiggly lines. And in some parts of the map, for example out here, out near I-10, there are relatively few lines and they're kind of straight. All of these lines represent the elevation differences of the area. And so we're going to discuss what these lines mean, how these maps are created, and how we can quickly look at them and use them to understand the three-dimensional nature, three-dimensional shape of the landscape. So first of all, let's start with just how are these lines created? How is a topographic map created? So let's consider this hypothetical landscape here with these three bumps. You can think of them as three mountains with valleys in between. What we want to do is figure out how we construct or how we go about building a topographic map and what the contour lines or topo lines mean. So let's consider a point on this landscape here. With few rare exceptions, it's always possible to go out on any point on the landscape and walk a path that stays at a constant elevation and eventually get back to where you started. It's always possible to walk a path that stays at the same elevation. You go sideways, and there might be a convoluted path, but it's always possible to walk a path that stays at the same elevation. You don't ever go uphill or downhill. So in this landscape, for example, if we start at this red point, and we walk in this direction, we have to go a little bit this way to avoid going down that valley, then back out around this mountain, back into this valley a bit, then around this mountain, then around the backside. Or in the other direction, we'd go in more or less a straight line and then around the backside of that mountain. So there's one path of constant elevation. Let's pick another point, let's say here, and do the same. So I'll walk to the right, I have to go into this valley and then back out, and then around this mountain, in this valley a bit, and then around this one. And in the other direction, it'd be more or less the straight line, and I would go around the backside of that mountain. So if we continue to do this, repeat this process at increasingly higher elevations, each line representing a specific elevation, it would look like this. So here are the corresponding topographic lines or contour lines drawn on this hypothetical landscape. Labeled with numbers, these might represent feet or meters, depending on which type of map that you're using. But in any case, each line represents the constant elevation. Everywhere along this line is 20 feet above some baseline, usually sea level. Nowhere along this line is any different. It's always 20 feet above sea level. Everywhere along this line is 40, etc. Each one of these lines represent a constant elevation, and in doing so, they contain together all of the three-dimensional nature of the landscape. But the clever thing is that we can then draw this picture on a flat piece of paper. So if I take this green image here with all of these lines and get rid of the green, it might look like this. Then if I take that and turn it on its side so we look at it directly from above, here it is. Here's the corresponding topographic map of this landscape. All of these lines represent the full three-dimensional nature of this landscape. So for example, this feature here corresponds to the top of this smaller mountain. This feature here corresponds to the top of that one. And this feature here corresponds to the top of that one, with the valleys here and here represented as such. So now let's take another example to look a little more closely on how a topographic map is made. So here we are with another simple example to try to better understand how a topographic map is made. So on the left here, what we're looking at is a hypothetical landscape. We're looking down from above in bird's eye view, so to speak, of a landscape. And imagine someone has gone out and measured the elevation a number of points on this landscape. So each of these numbers represents the elevation above some baseline. So for example, these 50 numbers might represent 50 feet above sea level. So a topographic map, or a topographic line is a line of constant elevation. It connects points all of the same elevation. And so if we wanted to draw the line representing 50 feet in elevation, it's been done for us in part, but I'm going to continue it here from this 50 point to this one, 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 and back to this one. Everywhere along that line is 50 feet above sea level. The corresponding 100 feet line here, 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 and here, etc. So if we do that for a bunch of elevations, what you end up with is a map, a topographic map like the one shown on the right. So this is a landscape feature which is roughly cone-shaped. Okay? A line, a number of circles on a topographic map indicate a cone-shaped feature in the landscape. You can think of this as a cone-shaped mountain. In this map, all of the points are at nice even numbers, 50, 100, 150, 200, etc. But it's not always like that, but we still can use the elevation of the landscape to construct a topo map, and you're going to be doing that sort of thing in the assignment. So let's take a look at that case. So here we are again in bird's eye view looking down in some hypothetical region. And our goal here is to draw a topographic map using the elevations provided. But notice they're not all at nice even numbers like 50 or 60 or 70. Some of them are, but there's also many at 62 and 84 and the like, and 96, etc. So we can still use this though to generate a topographic map. Here we're told that our contour interval is 5 feet. What that means is we want to label each line 5 feet different from its neighbor. I want a line at 50 feet, a line representing 55, 60, 65, etc. So I'm going to do a few of them here for you just to show you how this works. So first let's start with the line representing 50 feet in elevation. Here's a point representing 50 feet, so I'm going to start my line there. There it goes. Now I need to look around and figure out where to continue drawing this line. Now I don't see any points in the vicinity of 50 feet. However, I do see one of 57 and 47. 57 is above 50 feet, 47 is below. So in between them, 50 feet must exist somewhere. If I have points above and below, 50 must be somewhere in between, and it's closer to 47 than it is to 57. So approximately it must be there. So let's continue the line to the X. Now I look around again, and where do I go with my line? In this case, I see a point of 50 feet, so I can take it directly there. That was nice. Again, I look around. Where do I continue the line? I don't see any points of 50 feet in the immediate vicinity, but I do see one above and one below, 55 and 46, so 50 must be in between there, roughly in the middle there, maybe it's there, so I'll continue my line. There's another point of 50, there's another point of 50, there's another point of 50. But here again, I don't see a 50 anywhere nearby, but I see above and below, so 50 must be in between there, roughly there. There's another 50. Looking around, I don't see a 50, but I see a point above and below, so 50 must be in between those two. Then there's another 50. And there we're done. So 50 feet, that line represents 50 feet in elevation. Let's do another one at 60 feet. Here's 60 feet, so I'll start there. There's another 60, there's another 60. This one's pretty easy. There's 60, there's 60. Here's above and below, 64 and 56, and 60 is right in between those two, so I'll go there. There's a 60, there's a 60. That one was relatively simple. But let's do 65. So this one is 60 feet. So I'll do one more example to represent 65. So here's 70, here's 60. 65 is right in between those. So that point represents 65 feet. So my 65 feet topographic line must lie in between those two. So I'm going to march across the landscape looking for where to go. Here's a point above 65, here's a point below, so the 65 line must go between those two. There's a point of exactly 65, I'll head straight there. Again, I don't see any 65s in my vicinity now, but I do see a 67 and a 60, and 65 is between those two, but closer to 67. There's a 70 and a 60, and 65 is exactly in the middle of those. There's a 70 and a 64, so the 65 line must go between those two. Here's a 74 and a 70. Well, both of those are above 65, so I can't go there, but here's a 70 and a 60, and so 65 must be in between those two. And again, here's a 70 and a 60, and so the 65 line must go between those two. And we're done. The key is for drawing a contour line or topo line of a particular elevation, you're always going to be splitting elevation values that are larger and smaller than the line you're drawing. The 65 line goes through points that are 65, and it always goes through points that are higher on one side and lower on the other. So on topographic maps, usually it's the case that not all of the lines are labeled with their elevation. In our simple map, like this one on the left here, all of them are labeled, but usually they're not. And that's because imagine on our map of, say, the Tucson area with many topo lines. If they're all labeled, the map would be very messy. And so usually they're not all labeled. Usually it's the case like this image here shown on the right, where this one is labeled and this one is labeled, and the lines are also drawn bolder than the others. So these contours, the ones that are labeled, this one and this one, are referred to as index contours. And as we'll see later, even though the others aren't labeled, you can figure out what their elevation is. Here's another example of a topo map from the assignment to show how the labeling works. And so not all of the lines are labeled in this map, of course. And the index contours, the bold-faced ones, only a few are labeled, like this 800-foot line is labeled, this 900-foot line is labeled. And there's another one in there, that bold-faced one, which isn't labeled, but that's okay. You're still able to figure out what that elevation is, and I'll show you how to do that here next. So another feature of contour maps or topo maps is what's called the contour interval. It's the difference in elevation of two adjacent contour lines. And so like we said just a moment ago, not all the lines are labeled. Only some of them are. Those are called index contours. And so here's one. This one's labeled at, say, 700 feet, and this one's labeled at 800 feet. So I know between those two lines there's a 100 feet difference in elevation, 800 minus 700. So 800 minus 700 feet. So now the question is just to figure out how many even chunks, even divisions that 100 feet is divided into. In other words, how many contour lines are in between 700 feet and 800 feet. So if we start on the 700-foot line here and think of marching to the next one, there's 1, 2, 3, 4, 5 lines. It takes 5 lines to go from one index contour to another, 5 lines to go from 700 feet up to 800 feet in elevation. And so that 100 feet in elevation is divided into 5 equal chunks, and so that's 100 feet. The contour interval must be 20 feet. This line represents 700. This one is 20 more, 720. This one, is 20 more, 740. This one is 20 more, 760. This one is 20 more, 780. This one we already know is 800, so this one up here must be 820. Usually on topographic maps, like official ones that you might buy to use to go take on a hike, the contour interval is known, it's told to you on the map, but even if it isn't, you can figure it out. You just find 2 index contours, figure out how many lines are in between, do the division, and then you can know how different each contour line is. The topographic map also contains information about the steepness of the landscape, not just the elevations. So the contour lines and their corresponding elevations tells you how high or low some landscape feature is. But you can also quickly glance at the lines to get a sense of how steep it is, whether it's really steep from one point to the next, whether it's flat, etc. And so that has to do with the spacing of the contour lines. So notice on this sort of hypothetical landscape here, we have a steep slope on the left-hand side, and it kind of flattens out, and then it slopes down to the right, but not as steep. And so the corresponding contour map is shown here above, and notice how where the lines are close together, like here, that corresponds to a steep slope. Where the lines are not so close together, it corresponds to a less steep slope. And where the lines here are really far apart, that corresponds to a relatively flat spot. Contour lines close together indicates steepness. Contour lines far apart indicates not so steep or even flat. One really nice thing you can do with a topographic map is create what's called a topographic profile. In other words, it's a look at the shape of the landscape, how high it is, how low it is, how steep it is, how not so steep it is, from one point to another. All we need to do that is the map, a small piece of paper, and a pencil. And so here's how it works. So here's our topographic map of some hypothetical landscape. And let's say we wanted to take a hike from point A to point A primed. It'd be really nice to know whether that hike is flat, whether it's steep uphill in the beginning, steep downhill in the beginning, etc. We can do that. So how we do that is we take a small piece of paper, and I've shown here, and we lay it along that line. Here's the point A, and here's the point A prime. So we lay the piece of paper along that straight line, and everywhere where a contour line crosses that A to A prime line, like here, this contour line crosses our line, we put a little tick mark and write down the elevation of that line. Put a little tick mark, write down the elevation of that line. Here's another one. Put a little tick mark, write down the elevation of that line. And repeat for every contour line that we cross until we get all the way done with our little piece of paper and we've made it to A prime. Then we take that little piece of paper here, put it on the bottom of a piece of graph paper, and every tick mark that we have, for example this one, we have the corresponding elevation. We put a little dot at that elevation in the appropriate spot on the graph. Here's 180, we put a dot at 180. Here's 200, we put a dot at 200, etc. So if you do that for all of the dots, all the tick marks, and make all of the dots, and then connect those dots, you've made a topographic profile. This is the shape of the landscape from A to A prime. If we were to hike from A to A prime, we first would go slightly uphill to about here. Then we would go slightly downhill into a little valley, which corresponds to this feature. And then we'd have a relatively steady uphill hike all the way to A prime. This is called a topographic profile. It's a really neat, clever trick for extracting information from a topographic map.